planets don't need stars to survive. This breaks everything we thought we knew about how worlds form and live. You picture planets as loyal companions, always circling their parent stars in perfect harmony. That cozy family picture is completely wrong. Tonight we're discovering the cosmic outcasts that got kicked out of their homes, and why these wandering worlds might outnumber every planet you've ever heard of. Before we dive into these stellar refugees, drop a comment about where you're listening from. If you enjoy these cosmic mysteries, hit subscribe. These stories from the universe's dark corners deserve to be shared. Some planets break free from their stars. They rocket away from their birth homes and never come back. Scientists call these cosmic wanderers rogue planets. Think of them as the ultimate runaways. They've abandoned everything familiar and now drift alone through the vast emptiness between star systems. Astronomers discovered them by accident in the 1990s. They noticed starlight would suddenly get brighter for a few hours, then return to normal. Something invisible was bending that light as it passed between Earth and distant stars. That invisible something was a planet, but not just any planet. A world with no star of its own, traveling solo through interstellar space. Each discovery shattered our basic assumptions about how planets should behave. These rogue worlds have survived millions of years in complete isolation, proving that planets can thrive even after losing their stellar parents forever. Without a star, these worlds should be dead. No sunlight means no heat. No heat means everything freezes solid into cosmic S-balls. But rogue planets aren't dead at all. They're surviving in conditions that would seem completely impossible for any world we know. Picture the coldest place you can imagine. Now make it infinitely colder. Surface temperatures on these worlds drop close to absolute zero. That's the point where atoms barely move at all. Yet somehow, deep beneath their frozen surfaces, these planets maintain liquid oceans. Heat from their rocky cores keeps underground water flowing for billions of years. It's like having a campfire burning inside a block of ice. This means rogue planets could potentially harbor life in their hidden depths, making them some of the most mysterious worlds in our entire galaxy. Rogue planets come in every size imaginable. Some are smaller than Earth. Others dwarf Jupiter, the largest planet in our solar system. The smallest ones are probably rocky worlds like Earth or Mars. They got ejected from their star systems when they were still small and vulnerable. These cosmic pebbles now drift through space completely alone. The giants are the real monsters. Some rogue planets contain dozens of times more mass than Jupiter. They're so massive that they almost became stars themselves, but fell just short of igniting nuclear fusion in their cores. Scientists have detected rogue worlds spanning this entire range. From tiny rocky outcasts to gas giant behemoths, the universe has exiled planets of every possible description. The diversity suggests that planetary ejection happens at every stage of solar system formation, creating a hidden population of wandering worlds. Imagine living on a world where the sun never rises. Ever. That's the reality for any life that might exist on rogue planets. Surface temperatures plunge to nearly 400 degrees below 0 Fahrenheit. At these temperatures, the air itself would freeze solid and fall to the ground like snow. Any exposed water would instantly turn to ice harder than steel. But the real challenge isn't just cold. It's the complete absence of energy from above. Every ecosystem on Earth ultimately depends on sunlight for energy. Plants capture solar energy and convert it to food. Animals eat those plants. The entire food chain starts with our star. Rogue planets get zero energy from space. Any life that exists there would need to find completely different energy sources. Perhaps heat from radioactive decay deep inside the planet, or chemical energy from reactions between rocks and water. This creates possibilities for life unlike anything we've ever seen, adapted to eternal darkness and powered by the planet's own internal heat. Finding rogue planets is nearly impossible. They emit no light of their own and reflect no starlight. They're essentially invisible against the black backdrop of space. Astronomers had to get creative. They use a technique that Einstein predicted called gravitational lensing. Massive objects bend light rays as they pass nearby, acting like cosmic magnifying glasses. When a rogue planet drifts between Earth and a background star, its gravity bends the starlight toward us. This makes the distant star appear brighter for several hours as the planet acts like a natural telescope lens. These lensing events happen completely by chance. Astronomers monitor millions of stars simultaneously, waiting for the telltale brightening that reveals a hidden planet crossing our line of sight. Each detection provides clues about the rogue planet's mass and location, slowly building a census of the galaxy's wandering worlds. Early estimates suggest something incredible. Rogue planets might be far more common than planets that orbit stars normally. For every star in our galaxy, there could be multiple rogue planets drifting in the darkness between star systems. That would mean billions of wandering worlds inhabiting the spaces we thought were empty. This discovery would revolutionize our understanding of planetary formation. Instead of being rare cosmic accidents, planetary ejection might be a normal part of how solar systems evolve. Computer simulations support this possibility. When astronomers model the violent early history of planetary systems, they find that ejection events happen frequently. Most young solar systems lose at least one planet during their chaotic formation period. If these estimates prove correct, rogue planets represent a hidden majority in our galaxy's planetary population. Young planetary systems are war zones. Multiple giant planets form too close together, setting up inevitable gravitational battles that determine who stays and who gets expelled. The most common ejection mechanism involves what astronomers call three-body interactions. When three massive objects come close together, their combined gravity becomes chaotic and unpredictable. The lightest object usually gets launched away at tremendous speed, but planets can also be ejected through close encounters with passing stars. When another star approaches a young solar system, its gravity can disrupt planetary orbits and fling worlds into interstellar space. Some rogue planets might even form differently. Instead of forming around a star and getting ejected later, they might condense directly from gas clouds in space, becoming planetary orphans from birth. Each ejection mechanism creates rogue planets with different characteristics, adding to the diversity of these cosmic wanderers. Rogue planets aren't just drifting slowly through space. They're racing through the galaxy at incredible speeds, following paths completely independent of normal stellar motion. Most planets travel in predictable orbits around their parent stars, but rogue planets have broken free from these gravitational chains. They now follow ballistic trajectories through three-dimensional space like cosmic bullets fired from their birth systems. Their velocities can exceed 30 miles per second. That's fast enough to cross the entire United States in less than 2 minutes. These speeds carry them across vast interstellar distances over millions of years. Each rogue planet follows a unique trajectory through the galaxy. Some might loop back toward their birth regions, Others head straight for the galactic rim, never to return. This high-speed motion makes rogue planets incredibly difficult to study, as they quickly disappear from view after being detected. The most fascinating possibility about rogue planets involves what might be happening beneath their frozen surfaces. Despite the extreme cold above ground, these worlds could maintain liquid water oceans deep underground. Heat from radioactive decay in the planet's core could keep subsurface water liquid for billions of years. Just like Earth's core generates heat through radioactive elements, rogue planets might have enough internal energy to sustain hidden biospheres. Some rogue planets might also retain atmospheres that act as insulating blankets. Even without sunlight, a dense atmosphere could trap enough internal heat to keep surface temperatures above the freezing point of water. This creates the possibility of life forms adapted to eternal darkness. Instead of depending on photosynthesis like Earth's plants, life on rogue planets might derive energy from chemical reactions or thermal vents on the ocean floor. Such life would represent a completely independent genesis, evolved in isolation from any stellar influence. Rogue planets populate the vast spaces between stars that we once thought were empty. They're scattered throughout our galaxy's spiral arms, creating a hidden population of wandering worlds. Their distribution follows the galaxy's overall structure. More rogue planets exist in regions with higher star density, since those areas produce more planetary ejections during formation. The galactic center likely hosts enormous numbers of these cosmic outcasts. But rogue planets also venture into regions where normal planets could never exist. They drift through the cold vacuum between spiral arms and populate the galaxy's outer rim beyond the reach of stellar formation. This creates a three-dimensional map of wandering worlds throughout our galactic neighborhood. Every cubic light-year of space might contain multiple rogue planets, invisible to our current detection methods. The galaxy's true planetary census includes both the attached worlds we can see and these hidden populations of cosmic nomads. The discovery of rogue planets has forced astronomers to completely rethink planetary formation and evolution theories. These worlds challenge every assumption about how planets should behave and where they can survive. Traditional planetary science focused entirely on worlds orbiting stars. Rogue planets prove that stellar systems represent only part of the cosmic picture. Planets can exist and thrive in environments we never considered possible. This discovery also expands the potential for life in the universe. If rogue planets can maintain habitable conditions without stars, then the habitable zone concept becomes much more flexible. Life might exist in places we never thought to look. Future space missions will need to account for rogue planets when exploring interstellar space. These worlds could serve as stepping stones for future space exploration, providing resources and potentially even life forms in the vast emptiness between star systems. Rogue planets represent one of astronomy's most profound recent discoveries, revealing that our universe contains far more worlds than we ever imagined. What if some planets never had stars to begin with? This challenges everything we thought we knew about planetary birth. Most planets form in orderly disks around young stars. Gas and dust slowly clump together over millions of years. But some regions of space are so chaotic that planets can form completely independently. These are called primordial disk instabilities. Picture a massive cloud of gas spinning in space. Instead of forming one central star with planets around it, the cloud breaks apart into multiple chunks. Some chunks become stars. Others become planets that never find a stellar parent. This process happens during the earliest stages of star formation, when gravity hasn't yet organized everything into neat solar systems. The result is planets that are born as cosmic orphans from day one. These directly formed rogue planets tend to be especially massive, sometimes rivaling small stars in size. Can planets move closer to their stars over time? The answer is yes, and this migration often leads to disaster. Young planets don't stay in their original orbits. They interact with the leftover gas disk that surrounds their star. This creates friction that causes planets to spiral inward, like water circling a drain. Astronomers call this Type 2 migration. It affects the largest planets most severely. As these giant worlds move inward, they can disrupt the orbits of smaller planets in their path. Sometimes the migration becomes unstable. The migrating planet's orbit starts wobbling unpredictably. Eventually, gravitational interactions with other planets can sling it completely out of the star system. This means some rogue planets are failed migrants that got ejected during their journey toward their star. 3 planets can never stay stable when they come too close together. Physics makes this impossible. This is the most common way planets become rugs. When 3 massive worlds interact gravitationally, the system becomes chaotic. The planets' orbits become unpredictable, swinging wildly as they influence each other. The lightest planet always loses these encounters. It gets flung away at tremendous speed while the other 2 settle into stable orbits. This happens because momentum must be conserved. Energy from the chaotic interaction has to go somewhere. Computer simulations show this scenario playing out in most young planetary systems. The ejected planet can reach speeds of hundreds of miles per second, easily escaping its birth star's gravitational pull. These 3-body ejections create the fastest moving rogue planets in our galaxy. What happens when a foreign star invades someone else's planetary neighborhood? Complete destruction. Space isn't empty. Stars occasionally pass close to each other, especially in crowded regions of the galaxy. When a rogue star approaches an existing planetary system, its gravity acts like a cosmic wrecking ball. The intruder star doesn't need to hit anything directly. Its gravitational pull can stretch and distort planetary orbits from incredible distances. Planets that were once in stable, circular orbits suddenly find themselves on wild, elongated paths. Some planets get pulled toward the visiting star and captured as new family members. Others get flung in the opposite direction, rocketing away from both stars into interstellar space. These stellar encounters can destroy entire planetary systems in just a few thousand years, creating multiple rogue planets from a single catastrophic event. Binary stars are stellar couples that orbit each other. But when one partner dies, the surviving planets can become homeless refugees. About half of all stars exist in binary pairs, orbiting each other like cosmic dancers. Planets can form around both stars, creating complex multi-star family systems. The problems begin when one star evolves and changes mass. As stars age, they can swell up, explode, or collapse. Each of these events changes the gravitational balance that keeps planets in stable orbits. When a massive star explodes as a supernova, the blast can be lopsided rather than perfectly spherical. This asymmetric explosion gives the surviving companion star a kick that changes its motion through space. Planets orbiting the binary system suddenly find their gravitational anchor shifting unpredictably, often flinging them into the cosmic void as their stellar parents separate. When massive stars explode, they don't just destroy themselves. They can blast entire planets clear out of their solar systems. A supernova is one of the most violent events in the universe. In seconds, a star releases more energy than our sun will produce in its entire lifetime. This explosion doesn't happen evenly in all directions. The asymmetric blast creates what astronomers call a supernova kick. The explosion pushes the dying star's remnant in one direction. Any planets orbiting nearby get launched in the opposite direction, like balls shot from a cosmic cannon. These supernova-ejected planets become some of the fastest rogue worlds in existence. They can reach speeds exceeding 600 miles per second, fast enough to escape not just their home star system, but potentially even their home galaxy. The violence of their ejection also affects the planets themselves, potentially stripping away their atmospheres and moons during the explosive departure. Brown dwarfs are stars that never quite made it. They're too small to shine like real stars, but too big to be planets. And they can lose their planetary families just like regular stars. These failed stars form when collapsing gas clouds don't gather enough mass to ignite nuclear fusion. They end up as dim, cool objects that barely glow with leftover heat from their formation. Planets can form around brown dwarfs, just like they form around normal stars. But brown dwarfs are much lighter than real stars, making their gravitational grip on orbiting planets much weaker. When a brown dwarf encounters a normal star, the larger star's gravity can easily steal the brown dwarf's planets. The planets abandon their dim parent for the brighter, more massive star nearby. This creates a special category of rogue planets, worlds that once orbited failed stars but now drift freely through space after being stolen and then abandoned. In dense star clusters, planets change hands so frequently that they become cosmic trading commodities. Star clusters are neighborhoods where hundreds or thousands of stars lie packed closely together. The space between stars in these clusters is much smaller than in our sparse galactic region. This crowding creates a chaotic environment where stellar close encounters happen regularly. Planets get captured, traded, and ejected repeatedly as different stars pass near each other. A single planet might orbit 3 different stars during its lifetime in a dense cluster. Each gravitational handoff changes the planet's properties and orbital characteristics. Eventually, most cluster planets get ejected entirely when the cluster itself disperses. The stars spread apart over millions of years, leaving behind clouds of homeless planets scattered throughout the galaxy. Sometimes planets don't get ejected whole. They get smashed apart, creating rogue worlds from the wreckage. Large impacts between planets or asteroid-sized objects can completely destroy smaller worlds. The collision fragments scatter in all directions, some moving fast enough to escape their star system entirely. These impact-generated rogue planets are usually much smaller than normal rogue worlds. They're essentially large asteroids or moon-sized chunks of shattered planets now wandering alone through space. The most dramatic collisions can even affect gas giant planets. When 2 Jupiter-sized worlds collide, the impact can strip away their atmospheres and scatter their rocky cores across multiple star systems. Some scientists think this explains why we find so many small rogue objects in interstellar space. They're the debris from ancient planetary catastrophes. What happens when the cosmic glue holding young planetary systems together suddenly disappears? Chaos erupts. Young star systems are surrounded by massive disks of gas and dust left over from the star's formation. This gas disk helps keep planetary orbits stable by damping out small irregularities before they can grow. But gas disks don't last forever. After about 10 million years, the central star's radiation blows away most of the remaining gas. This removes the stabilizing influence that kept the planets in orderly orbits. Without the gas disk damping effect, small gravitational interactions between planets can grow into major instabilities. Planets that lived peacefully together for millions of years suddenly begin affecting each other's orbits more strongly. This disk dispersal phase often triggers the final ejection events that create rogue planets, as the newly unstable system reorganizes itself into a more stable configuration. Planets with tilted orbits face a deadly problem. Their paths become increasingly unstable over time until something catastrophic happens. Most planets orbit their stars in neat, flat circles, but some planets have tilted orbits that are angled compared to their star's equator. This tilt creates a slow-motion disaster called the Kozai mechanism. Here's how it works. The tilted planet's orbit gradually changes shape over thousands of years. Sometimes it becomes more circular. Other times it stretches into a long, narrow ellipse that brings the planet dangerously close to its star. During the closest approaches, the planet experiences extreme gravitational forces. These forces can either pull the planet into its star or fling it completely out of the system. This tilted orbit instability explains why many rogue planets were ejected from systems where they once had stable homes. Every planet lives inside an invisible sphere of gravitational influence. Breaking free from this sphere is the key to becoming a rogue planet. Astronomers call this boundary the Hill sphere. It's the region around each planet where that planet's gravity dominates over its star's gravity. Think of it as each planet's personal gravitational territory. Inside the Hill sphere, the planet controls what happens. Moons, rings, and small asteroids stay bound to the planet. Outside the Hill sphere, the star's gravity takes over, and anything there will eventually orbit the star instead. For a planet to become rogue, it must gain enough speed to break completely through its Hill sphere boundary. This requires tremendous energy, usually from violent gravitational encounters with other massive objects. Once a planet crosses this invisible line, there's no gravitational force strong enough to pull it back home. There are special points in space where gravitational forces perfectly balance. But these balance points are dangerously unstable traps for planets. These locations are called Lagrange points. They exist wherever the gravity from a star and a large planet cancel each other out exactly. Small objects can sit at these points without being pulled toward either massive body. The problem is that these balance points are like trying to balance a pencil on its tip. Any tiny disturbance causes everything to collapse rapidly. A passing asteroid, a small gravitational wave, or even the solar wind can trigger catastrophic instability. When the balance breaks, objects near these points get accelerated in completely unpredictable directions. Some crash into the star or planet. Others get launched into chaotic orbits that eventually lead to ejection from the system. This Lagrange point instability can transform orderly planetary systems into gravitational war zones within just a few thousand years. Sometimes planets get hit with gravitational forces so intense they change everything in just hours or days. This happens during what astronomers call impulse approximation events. Picture a planet minding its own business in a stable orbit. Suddenly, a massive object passes nearby at high speed, delivering a powerful gravitational punch. The encounter happens too quickly for gradual changes. Instead, the passing object's gravity acts like a cosmic baseball bat, instantly changing the planet's speed and direction. The entire interaction might last only a few days. But those few days are enough to completely alter the planet's fate. A planet that was safely orbiting its star for millions of years can suddenly find itself on an escape trajectory, heading for interstellar space. These rapid gravitational encounters create some of the fastest moving rogue planets, launched with tremendous kinetic energy from their brief but violent interactions. When three planets come close together, it becomes a cosmic game of billiards. And just like in billiards, someone always gets knocked off the table. This three-body scattering creates the most common type of planetary ejection. Two planets approach each other on crossing orbits. Their mutual gravity changes both of their paths, usually sending one planet inward toward the star and the other outward. The inward-moving planet often gets captured in a closer, more stable orbit. The outward-moving planet gains so much speed that it escapes the star system entirely. This creates one winner and one loser from every three-planet encounter. Computer simulations show this billiard ball effect happening repeatedly in young planetary systems. Each encounter removes one planet from the family, until only the most stable orbits remain. The ejected planets carry away excess energy from the system, allowing the remaining planets to settle into the orderly arrangements we observe today. Planetary systems operate like cosmic stock markets. Planets constantly trade orbital energy and rotational momentum with each other. In these energy exchanges, some planets become buyers that gain energy and move to higher, more distant orbits. Others become sellers that lose energy and spiral closer to their star. The planets that lose the most energy often get ejected entirely. This energy trading happens through gravitational interactions over millions of years. No actual contact is needed. Planets can exchange energy from millions of miles apart through their gravitational fields. The trading system follows strict conservation laws. Energy and momentum can't be created or destroyed, only transferred from one planet to another. This means every ejection event requires at least one planet to gain energy while another loses it. The planets that become rogue worlds are essentially the biggest losers in this cosmic energy market, forced to abandon the system when they run out of gravitational currency. Some planetary systems operate like cosmic orchestras. The planets orbit their star in mathematical ratios that create perfect gravitational harmony. These orbital resonances happen when planets complete their orbits in simple ratios like 2:1 or 3:2. For example, one planet might orbit twice for every single orbit of another planet. This creates a repeating pattern of gravitational interactions. Resonances can be stable for millions of years, keeping planets locked in predictable dance patterns. But they're also extremely fragile. Any disruption that breaks the resonance can trigger immediate chaos. When resonance breaks, the planets that were once in perfect harmony suddenly start affecting each other's orbits unpredictably. The system quickly reorganizes itself, often ejecting one or more planets to restore stability. These resonance breakups explain why many rogue planets come from systems that appeared perfectly stable for long periods before suddenly becoming violent. Not all planetary ejections happen quickly. Some are slow-motion catastrophes that unfold over geological timescales. This process is called secular evolution. Small gravitational influences accumulate gradually over millions of orbital periods. Each influence is tiny by itself, but they add up like compound interest in a bank account. The changes are so slow that they're invisible on human timescales. A planet's orbit might shift by just a few degrees per million years, but eventually, these tiny changes reach a critical threshold where the system becomes unstable. Once the threshold is crossed, the accumulated instability releases suddenly. Planets that lived peacefully together for hundreds of millions of years can be ejected within just a few thousand years. This secular evolution explains why some rogue planets were ejected from very old, mature star systems that seemed completely stable. Certain regions of planetary systems are cosmic danger zones. Any planet that wanders into these areas faces almost certain ejection. These chaotic zones exist wherever multiple planets' gravitational influences overlap strongly. The combined gravity creates such complex force patterns that planetary motion becomes completely unpredictable, even with the most powerful computers. A planet entering a chaotic zone might orbit normally for thousands of years, then suddenly veer off in a completely random direction. There's no way to predict when or how the chaotic behavior will begin. The unpredictability comes from extreme sensitivity to tiny changes. A difference of just 1 inch in a planet's position can lead to completely different outcomes millions of years later. Most chaotic zones eventually clear themselves out by ejecting any planets unlucky enough to enter them, leaving behind more stable orbital configurations. Every star system has an invisible speed limit. Planets that exceed this limit become permanent exiles. This critical speed is called escape velocity. It's the minimum speed needed to break free from a star's gravitational pull forever. For our solar system, escape velocity is about 26 miles per second at Earth's distance from the Sun. Planets normally travel much slower than escape velocity. Earth orbits at just 19 miles per second. Fast enough to stay in orbit, but not fast enough to escape. Most planets are similarly trapped by their relatively low orbital speeds. To become rogue, a planet must somehow gain the extra speed needed to exceed escape velocity. This usually happens during violent gravitational encounters that act like cosmic slingshots. Once a planet breaks the speed limit, there's no force in the universe strong enough to slow it down and bring it home. The universe keeps perfect books. Every planetary ejection must balance the cosmic accounting ledger of momentum conservation. When a planet gets ejected from its star system, its momentum doesn't just disappear. The total momentum of all objects in the system must remain constant before and after the ejection event. This means ejecting a planet in one direction requires pushing something else in the opposite direction. Usually, the remaining planets shift slightly in their orbits to compensate for the momentum carried away by the ejected world. The conservation law also determines how fast rogue planets move and in which directions they travel. These aren't random. They're precisely calculated by the universal accounting system that tracks every unit of momentum. This momentum bookkeeping explains why computer simulations can predict the statistical properties of rogue planet populations, even though individual ejection events seem chaotic. Scientists can't watch planetary ejections happen in real time. These events take millions of years to unfold. Instead, they use supercomputers to fast-forward through cosmic history. These n-body simulations track the gravitational interactions between multiple planets over billions of years of simulated time. The computers solve the same mathematical equations that govern real planetary motion. Running these simulations reveals patterns that would be impossible to discover through observation alone. Scientists can watch thousands of virtual planetary systems evolve, cataloging how often ejections occur and what conditions make them most likely. The simulations also let scientists test different theories about planetary formation and evolution. By changing the starting conditions, they can see which scenarios produce the most rogue planets. These computer experiments have revolutionized our understanding of planetary system dynamics, showing that ejection events are not rare accidents, but inevitable consequences of gravitational physics. Rogue planets are completely invisible to normal telescopes. They emit no light and reflect no starlight from nearby stars. Yet astronomers have found a way to detect them using the universe's own magnifying glasses. The technique is called gravitational microlensing. It works because massive objects bend light rays as they pass nearby. When a rogue planet crosses between Earth and a distant star, the planet's gravity acts like a lens. This gravitational lens makes the background star appear brighter for several hours or days. The star's light gets focused toward Earth, creating a temporary brightening that follows a very specific pattern. The brightening curve tells astronomers everything they need to know. The duration reveals the planet's mass. The shape of the curve shows whether it's alone or has companions. This cosmic magnifying effect is the only way to find rogue planets floating in the darkness between star systems. Some stars wobble slightly as they move through space. These tiny wobbles reveal the presence of invisible companions tugging on them gravitationally. This detection method is called astrometry. Astronomers measure star positions with incredible precision, looking for periodic shifts that indicate orbital motion around an unseen object. When a star has an invisible companion, both objects orbit around their common center of mass. The star traces a small ellipse in the sky as it completes each orbit. Advanced telescopes can detect these miniature stellar dances. If the companion is too dim to see but too massive to be a planet orbiting the star normally, it might be a rogue planet that got captured. The orbital motion reveals the hidden world's presence and mass. This technique works best for nearby stars where the tiny positional changes are easier to measure accurately. Young rogue planets glow with leftover heat from their formation. This faint infrared radiation makes them visible to specialized space telescopes designed to detect heat rather than visible light. These planets are still warm because they formed recently in cosmic terms. They're less than 100 million years old, which means they haven't had time to cool down completely. Infrared telescopes can photograph these warm rogue planets directly, capturing actual images of worlds drifting alone through space. The planets appear as dim red dots against the cold background of interstellar space. Direct imaging works only for the youngest and largest rogue planets. Older planets have cooled too much to detect, and smaller planets don't generate enough heat to photograph. This method has discovered several massive rogue planets in nearby star-forming regions where young worlds are most common. How do you count objects you can't see? Astronomers use statistical analysis to estimate how many rogue planets exist based on the few they manage to detect. Each microlensing detection represents thousands of rogue planets that remain hidden. Scientists can calculate this hidden population by analyzing the rate of detection events and the survey area covered by their telescopes. The math works like sampling a large population through random encounters. If you detect one rogue planet in a certain volume of space, statistical models can estimate how many more exist in similar regions throughout the galaxy. Different types of events reveal different categories of rogue planets. Short-duration events indicate small planets. Long-duration events suggest massive worlds. The distribution pattern reveals the overall population structure. This statistical approach has suggested that rogue planets might outnumber normal planets by significant factors. Distance measurement is crucial for understanding rogue planets. But how do you measure the distance to an invisible object? Astronomers use parallax measurement, the same technique surveyors use to measure distant mountains. As Earth orbits the Sun, nearby objects appear to shift position relative to background stars. During a microlensing event, astronomers can sometimes detect this parallax shift. The apparent position of the lensing effect changes slightly as Earth moves along its orbit during the months-long observation period. The amount of parallax shift reveals the distance to the rogue planet. Closer planets show larger shifts. More distant planets show smaller shifts. This geometric relationship allows precise distance calculations. Knowing the distance and the lensing effect's strength allows astronomers to calculate the rogue planet's actual mass and orbital speed. Nearby rogue planets move noticeably across the sky over time. This motion helps astronomers distinguish them from distant background stars that appear stationary. This detection technique focuses on proper motion, the angular movement of objects across the sky. Most background stars are so distant that their proper motion is undetectable, but nearby rogue planets can show significant motion over months or years. Advanced surveys photograph the same sky regions repeatedly over long periods. Computer programs compare the images, looking for objects that have moved between observations. Objects showing high proper motion are candidates for nearby rogue planets. Follow-up observations can determine whether they're actually planetary mass objects rather than distant stars or brown dwarfs. This method works best for rogue planets within a few dozen light-years of Earth, where their motion is most apparent. Rogue planets have distinctive colors that help astronomers identify them among other dim objects in space. Cold rogue planets appear extremely red in infrared surveys. They're much redder than normal stars or even brown dwarfs. This distinctive color signature acts like a cosmic fingerprint that reveals their planetary nature. The red color comes from their low surface temperatures. These worlds are so cold that they emit most of their energy at very long infrared wavelengths, making them appear deep red in astronomical images. Astronomers create color magnitude diagrams that plot objects' brightness against their colors. Rogue planets occupy a specific region of these diagrams, separated from stars and brown dwarfs by their extreme red colors. This color selection technique helps astronomers identify rogue planet candidates in large sky surveys containing millions of objects. Finding rogue planets requires continuous monitoring of vast sky regions. No single telescope can do this job alone. Coordinated survey networks use multiple telescopes around the world to watch the same star field simultaneously. When one telescope detects a potential microlensing event, others can immediately confirm and monitor the event. This global coordination is essential because microlensing events are unpredictable and brief. They can begin without warning and last only days or weeks. Missing the peak brightness could mean losing crucial data about the rogue planet. Different telescopes contribute different capabilities. Some provide continuous monitoring. Others offer high-resolution follow-up observations. Space-based telescopes avoid weather interruptions that plague ground-based observations. These coordinated campaigns have dramatically increased the detection rate of rogue planets by ensuring comprehensive coverage of microlensing events. Each rogue planet detection represents a much larger hidden population, Astronomers use event rates to estimate how many undiscovered rogue planets exist in our galaxy. The calculation starts with detection statistics. If survey telescopes find one rogue planet per year while monitoring a certain number of background stars, mathematical models can extrapolate to the entire galaxy. The models account for detection bias, the fact that surveys preferentially find the most massive rogue planets because they create stronger lensing effects. Smaller planets are much harder to detect, so their numbers must be estimated statistically. Event rate analysis suggests that billions of rogue planets populate our galaxy. Some estimates indicate they may outnumber attached planets by factors of 2 or more. These population estimates drive planning for future space missions designed to study rogue planets in greater detail. The duration of microlensing events reveals crucial information about rogue planets. Longer events indicate more massive planets, while shorter events suggest smaller worlds. This duration analysis works because massive planets create stronger gravitational lensing effects that last longer. A Jupiter mass rogue planet might brighten a background star for several weeks. An Earth mass planet might cause brightening lasting only a few days. The event duration also depends on the planet's speed across the line of sight. Faster moving planets create shorter lensing events because they pass by more quickly. Slower planets linger longer, creating extended brightening periods. By combining duration measurements with other observational data, astronomers can simultaneously determine both the mass and velocity of rogue planets. This provides crucial insights into how these worlds were ejected from their birth systems. Duration analysis has revealed that rogue planets span an enormous range of masses and speeds, reflecting the variety of ejection mechanisms that created them. Current ground-based surveys have found only dozens of rogue planets. The Roman Space Telescope will revolutionize this field by discovering thousands of these wandering worlds. This next-generation infrared space observatory will conduct an unprecedented survey of the galactic center region. Its location in space eliminates atmospheric interference that limits ground-based telescopes. The Roman telescope's advanced detector can monitor 200 million stars simultaneously, watching for the brief brightenings that indicate rogue planet transits. This represents a 100-fold increase in survey capability compared to current facilities. Computer models predict the Roman survey will detect over 1,000 rogue planets during its primary mission. This enormous sample will finally provide statistical certainty about rogue planet populations and properties. The mission will also discover rogue planets in previously unexplored regions of the galaxy, revealing how these wandering worlds distribute throughout different stellar environments. Modern rogue planet surveys generate far more data than human astronomers can analyze. Artificial intelligence systems now do most of the actual planet hunting. Machine learning algorithms scan through millions of stellar light curves, looking for the subtle patterns that indicate microlensing events. These AI systems can analyze data thousands of times faster than human researchers. The algorithms learn to recognize genuine rogue planet signals by training on libraries of confirmed detections. They become increasingly sophisticated at distinguishing real events from instrumental noise or stellar variability. Advanced AI systems can even classify different types of lensing events automatically. They separate single rogue planets from binary systems, estimate masses, and flag unusual events for human follow-up. This automation is essential for future surveys that will generate petabytes of astronomical data, requiring real-time analysis to catch fleeting rogue planet transits. In 2016, astronomers detected something unprecedented: a planet roughly the size of Earth, drifting completely alone through space with no star to call home. The discovery came from a project called OGLE, a Polish survey that monitors millions of stars for gravitational lensing events. On one ordinary night, they noticed a distant star brighten unexpectedly, then fade back to normal over several hours. This brief brightening followed the exact pattern predicted for a rogue planet crossing between Earth and the background star. The planet's gravity had acted like a cosmic magnifying glass, focusing the star's light toward our telescopes. Scientists named the invisible world OGLE 2016 BLG 1928. The long designation identifies exactly when and how it was found. The numbers and letters tell the story of humanity's first confirmed detection of an Earth-mass rogue planet. This single detection proved that planets as small as Earth can survive ejection from their birth systems and continue wandering through interstellar space indefinitely. Some rogue planets are hot enough to photograph directly. Piso J3 is one of these glowing outcasts, visible to infrared telescopes as a dim red dot against the darkness of space. This massive world contains about 6 times as much material as Jupiter. But unlike Jupiter, it has no star to orbit. It drifts alone through a nearby star-forming region, glowing with leftover heat from its violent formation. The planet is young by cosmic standards, only 12 million years old. It's still hot enough from its recent birth to emit significant infrared radiation, making it one of the few rogue planets that can be photographed directly. Infrared images show PSO J3 as an isolated point of heat moving slowly against the background stars. Its surface temperature reaches 1800 degrees Fahrenheit, hot enough to melt copper but cool enough to maintain a solid surface. This direct imaging proves that massive rogue planets can be studied in detail, providing crucial insights into how these cosmic outcasts form and evolve. Where does a planet end and a failed star begin? CFB DR2149 sits right on this cosmic boundary, challenging astronomers to decide what category it belongs in. This mysterious object contains about 4 times as much mass as Jupiter. That makes it too small to be a brown dwarf, a failed star that never achieved nuclear fusion. But it might be too large to be called a true planet. The object shows no signs of stellar nuclear reactions in its core. It generates heat only from gravitational compression and leftover formation energy. This suggests it formed more like a planet than a star, despite its massive size. CFB DSIR-2149 drifts alone through space with no stellar companion, making it a rogue regardless of its exact classification. Its temperature and brightness fall between typical planets and typical brown dwarfs. This boundary-walking object forces scientists to reconsider the definitions that separate planets from stars, highlighting how rogue worlds can challenge our cosmic categories. 2MS's J1 1911-37 represents the extreme cold end of the rogue planet spectrum. This world is so frigid that it barely registers on infrared surveys, glowing weakly with the faintest possible heat signature. The planet's surface temperature hovers around -400 degrees Fahrenheit. That's only about 100 degrees above absolute zero, the coldest temperature possible in the universe. At these temperatures, even hydrogen gas would freeze solid. Despite this extreme cold, the planet still emits enough infrared radiation to be detected by sensitive space telescopes. This faint glow comes from radioactive decay deep in the planet's core, providing just enough energy to keep it barely visible. The world likely lost its original heat billions of years ago, settling into thermal equilibrium with the cosmic microwave background. It now represents what most old rogue planets probably look like: ancient, cold, and nearly invisible. 2ms J-Well in 1911-37 demonstrates that rogue planets can survive and remain detectable even after cooling for enormous periods in the depths of space. WISC J85510.83 confuses astronomers by displaying characteristics of both planets and failed stars. This cosmic rebel refuses to fit neatly into any standard classification system. Spectroscopic analysis reveals that the object has a mass in the planetary range, probably less than 10 times Jupiter's mass, but its other properties more closely resemble a brown dwarf, a type of failed star that never achieved nuclear fusion. The confusion arises because WISC A520A3 formed in isolation, without orbiting a normal star. It condensed directly from a collapsing gas cloud, more like a star than a planet. But it didn't gather enough mass to ignite nuclear reactions. Astronomers classify it as a white dwarf, the coolest type of brown dwarf known. Yet its low mass suggests it might be better described as a supermassive rogue planet that formed through stellar rather than planetary processes. This classification puzzle highlights how rogue worlds challenge traditional boundaries between planets, brown dwarfs, and stars. Maui 2007 BLG92 holds the distinction of being one of the first rogue planets with a precisely measured mass. This detection helped establish the statistical properties of the wandering planet population. The lensing event lasted about 3 weeks, indicating a planet several times more massive than Earth. Detailed analysis of the brightening curve revealed a mass roughly 3.3 times that of our home planet, placing it firmly in the super-Earth category. This mass measurement was crucial for understanding rogue planet demographics. It proved that ejected worlds span a continuous range from Earth-sized to Jupiter-sized, with no obvious gaps in the mass distribution. The detection also provided insights into rogue planet velocities. Maui 2007 BLG 92 moves through space at about 30 miles per second relative to nearby stars, typical for objects ejected during violent planetary system formation. This single well-characterized detection helped validate theoretical models of planetary ejection and establish benchmarks for interpreting future discoveries. OG 2012 BLG's 0950 was more important for what it represented than for what it was individually. This detection helped prove that Jupiter-mass rogue planets populate our galaxy in enormous numbers. The planet itself is unremarkable, a gas giant roughly similar to Jupiter in mass and composition. But its detection came as part of a systematic survey that monitored thousands of stars simultaneously over several years. Statistical analysis of this and similar detections revealed that rogue planets are surprisingly common. The survey results suggested there might be billions of wandering Jupiter-mass worlds in our galaxy alone. This statistical breakthrough transformed rogue planets from exotic curiosities into a major component of galactic planetary populations. The numbers suggested that planetary ejection is a normal, even inevitable, part of solar system evolution. OGL 2012 BLG's 0950 thus became a cornerstone discovery that established rogue planets as a fundamental aspect of cosmic architecture rather than rare accidents. Che 1009-13 lurks in the Chameleon star-forming region, a cosmic nursery where new stars and planets are still being born. But this world appears to be a planetary orphan with no stellar parent. The object has a mass about 8 times that of Jupiter, placing it at the boundary between planets and brown dwarfs. It shows clear signs of youth, glowing with heat from its recent formation in the stellar nursery. What makes Che 1109-13 unusual is its location. Most rogue planets are found in older regions of the galaxy, far from active star formation. This world seems to have formed recently, but immediately became homeless. The object might represent a first-generation rogue planet, one that was ejected during the chaotic early phases of stellar nursery evolution, before the region settled into stable stellar systems. CHA 10913 provides a rare glimpse of planetary ejection happening in real time within active star-forming environments. HD 6906b occupies an extremely unusual orbit that may represent the final stage before becoming a true rogue planet. This world sits at the very edge of its star system, barely held by its parent star's gravity. The planet orbits at a distance 50 times greater than Earth's distance from the Sun. At this extreme range, the gravitational bond between planet and star is incredibly weak. Any small disturbance could break the connection entirely. Computer simulations suggest that HD 16906b is slowly spiraling outward, gradually escaping its star's gravitational influence. Over millions of years, it will likely become a true rogue planet, cut loose from its stellar anchor. The planet's current precarious position offers astronomers a unique opportunity to study the final stages of planetary ejection. It represents a snapshot of a world in transition from attached planet to cosmic wanderer. HD 16906b demonstrates that the boundary between orbiting planets and rogue planets isn't always clear-cut. Some worlds exist in liminal states between the two categories. SIMPJA 3656 stands out among rogue planet candidates for its extraordinary magnetic field and mysterious radio emissions. This world generates radio signals powerful enough to detect from Earth. The object appears to be about 12 times more massive than Jupiter, placing it near the upper limit for planetary masses. Despite having no star to interact with, it produces intense radio bursts that repeat in a regular pattern. These radio emissions probably come from charged particles spiraling around the planet's magnetic field lines. The magnetic field must be incredibly strong, possibly 200 times more powerful than Jupiter's already impressive field. The regular timing of the radio pulses suggests the planet rotates very rapidly, completing one full rotation in just a few hours. This fast spin might help generate and maintain the planet's powerful magnetic field. SIMPJA 3066 proves that rogue planets can remain magnetically active long after leaving their birth systems, potentially maintaining dynamic atmospheric and magnetic phenomena for millions of years. Every detected rogue planet represents thousands of others hiding in the darkness. Scientists use these rare discoveries to build a complete census of the galaxy's wandering worlds. The process works like counting wildlife in a vast forest by tracking footprints. Each microlensing detection provides clues about the overall population. How many planets exist at different mass ranges throughout our galactic neighborhood? Astronomers create mass functions that show how rogue planet numbers change with size. Smaller planets appear to be far more common than massive ones, following the same pattern seen in normal planetary systems. The mass function reveals a continuous distribution from sub-Earth worlds all the way up to objects nearly massive enough to be stars. There are no obvious gaps or preferred sizes in the rogue planet population. This statistical mapping technique transforms individual discoveries into comprehensive understanding of how many wandering worlds populate different regions of our galaxy. Could there be more homeless planets than planets with stellar families? Recent surveys suggest this incredible possibility might be true. Current estimates indicate our galaxy contains between 200 billion and 400 billion rogue planets. That's roughly one wandering world for every star in the Milky Way, and possibly many more than the number of planets still orbiting their parent stars. This potential majority population remained completely hidden until the development of gravitational lensing surveys in the 1990s. For most of human history, we knew nothing about the galaxy's largest planetary population. The numbers come from extrapolating microlensing detection rates across the entire galaxy. If confirmed, these estimates would revolutionize our understanding of planetary system evolution and cosmic architecture. Rogue planets might represent the universe's dominant planetary population, making attached planets like Earth the unusual minority rather than the cosmic norm. Below the detection threshold of current surveys lies a hidden universe of tiny rogue worlds. These sub-Earth vagabonds probably outnumber larger planets by enormous factors. Gravitational lensing surveys preferentially detect the most massive rogue planets because they create the strongest lensing effects. Planets smaller than Earth produce such weak signals that they usually escape detection entirely. Theoretical models suggest the smallest rogue objects, Mars-sized worlds and smaller, could number in the trillions throughout our galaxy. These cosmic pebbles were likely ejected during the violent formation phases of planetary systems. Some of these tiny wanderers might be fragments of larger worlds that were shattered during catastrophic collisions. Others could be small planets that simply lost their gravitational battles with larger siblings during system formation. The existence of this invisible population would mean that rogue planets collectively contain an enormous amount of mass. Space between the stars isn't uniformly populated with wandering planets. These cosmic nomads cluster in specific regions where conditions favor their survival and detection. Rogue planet density varies dramatically across the galaxy. Some regions contain dozens of wandering worlds per cubic parsec, a volume of space about 20 light-years on each side. Other regions appear nearly empty of vagrant planets. The highest concentrations occur near the galactic center, where stellar densities are greatest. This crowded environment produces more planetary ejections and also provides more background stars for gravitational lensing detection. Lower densities exist in the galaxy's outer regions and in the spaces between spiral arms. These cosmic suburbs have fewer stars and therefore generate fewer rogue planets during stellar system formation. Understanding this spatial distribution helps astronomers predict where future surveys will be most successful at discovering new populations of wandering worlds. How often do star systems eject their planetary children? Computer models suggest that most solar systems lose at least one planet during their violent youth. The ejection rate depends on several factors. Systems with multiple giant planets experience more gravitational chaos and produce more rogues. Single-planet systems rarely eject their lone worlds unless external forces intervene. Simulations indicate that systems like our early solar system typically eject between 1 and 3 planets during their first 100 million years of evolution. The exact number depends on the initial arrangement and masses of the forming planets. Binary star systems, where 2 stars orbit each other, show higher ejection rates due to the additional gravitational complexity. These systems can destabilize and eject entire planetary families when the stellar orbits change. This steady production of rogue planets throughout galactic history explains why wandering worlds have accumulated into such enormous populations over billions of years. Rogue planets don't all move at the same speed through space. They follow a complex distribution of velocities that reveals their diverse ejection histories. The velocity distribution of rogue planets spans an enormous range. Some cruise through space at relatively sedate speeds of just a few miles per second. others rocket along at hundreds of miles per second, fast enough to cross the entire United States in under 2 minutes. The fastest rogues were likely ejected by supernova explosions or close encounters with massive stars. These high-speed refugees carry tremendous kinetic energy as they traverse interstellar space. Slower rogues probably escape through gentler three-body interactions during normal planetary system evolution. Their modest speeds allow them to remain within their birth regions of the galaxy for long periods. This velocity spread creates a three-dimensional traffic pattern throughout the galaxy, with rogue planets following ballistic trajectories in all directions at widely varying speeds. Rogue planet populations have changed dramatically over our galaxy's 13-billion-year history. The rate of planetary ejection has varied as stellar formation rates and galactic conditions evolved. In the early universe, when star formation was at its peak, planetary ejection rates were probably much higher than today. Young, crowded stellar neighborhoods produced violent interactions that launched planets into space at unprecedented rates. As the galaxy aged and star formation slowed, ejection rates declined accordingly. Fewer new planetary systems meant fewer opportunities for gravitational chaos and planetary exile. The current population of rogue planets represents the accumulated result of billions of years of ejection events. Older rogues have had time to cool and become nearly invisible, while younger ones still glow with formation heat. This age-dependent evolution means that future astronomical surveys might discover evidence of ancient rogue populations that date back to the galaxy's most active star-forming epochs. Stars with different chemical compositions produce different numbers of rogue planets. This metallicity dependence reveals how stellar chemistry affects planetary system stability. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. Stars with higher metallicity tend to form more planets, but they also tend to create more unstable planetary systems. Metal-rich stars produce larger planets that interact more violently during system formation. These massive worlds are more likely to engage in gravitational battles that result in planetary ejection. Metal-poor stars typically form smaller, less interactive planetary systems. Their planets are more likely to remain in stable orbits throughout their lifetimes, producing fewer rogues. This chemical dependency means that different regions of the galaxy, which formed at different times with different chemical compositions, host varying populations of wandering worlds. Crowded stellar environments act like cosmic blenders, mixing planetary systems and creating enormous numbers of homeless worlds. Dense star clusters and the galactic center represent these high-activity zones, when hundreds or thousands of stars lie packed closely together. Planetary systems frequently interact and exchange members. In these environments, planets regularly get traded between different stars, captured into new orbits, or ejected entirely. A single planet might change stellar parents multiple times before finally becoming a permanent rogue. The galactic center experiences the most extreme version of this process. The supermassive black hole's gravity, combined with extremely high stellar densities, creates chaos that produces rogue planets at accelerated rates. These environmental hotspots contribute disproportionately to the galaxy's overall rogue planet population despite representing relatively small volumes of space. Current surveys probably miss the majority of rogue planets that actually exist. Detection methods have built-in biases that systematically undercount the wandering world population. Woof. Gravitational lensing preferentially detects massive planets moving at specific speeds and distances. Planets that are too small, too fast, too slow, or too distant simply don't create detectable lensing events. Geographic bias also affects detection rates. Most surveys monitor stars toward the galactic center, where background star densities are highest. This leaves vast regions of the galaxy completely unexplored for rogue planets. Timing bias compounds the problem. Lensing events are brief and unpredictable. Many rogue planets undoubtedly pass through survey fields when telescopes aren't watching or weather conditions prevent observations. These systematic biases mean that true rogue planet numbers could be much higher than current estimates suggest, potentially by factors of 10 or more. Future space missions will discover rogue planets at unprecedented rates, finally providing accurate counts of the galaxy's wandering world population. The Roman Space Telescope will monitor 200 million stars simultaneously, increasing detection rates by factors of hundreds compared to current ground-based surveys. Its space-based location eliminates weather and atmospheric interference. Advanced machine learning algorithms will process the enormous data streams in real time, identifying rogue planet candidates faster than human astronomers ever could. These AI systems will dramatically improve detection efficiency. Infrared surveys will complement lensing detection by directly photographing warm rogue planets. These thermal sensors will reveal populations invisible to gravitational lensing techniques. Within the next decade, these technological advances should increase known rogue planet discoveries from dozens to thousands, finally providing statistical certainty about how many wandering worlds populate our galactic neighborhood. Surface temperatures on rogue planets plunge to nearly absolute zero. This represents the coldest possible environment where matter can exist in the universe. Absolute zero sits at minus 459 degrees Fahrenheit. At this temperature, atoms barely move at all. Most rogue planets hover only slightly above this cosmic temperature limit, making them among the coldest objects in existence. Without a star's heat, these worlds lose their warmth through radiation into empty space. The process continues for billions of years until the planet reaches thermal equilibrium with the cosmic microwave background, the faint afterglow of the Big Bang. At these extreme temperatures, familiar substances behave in completely alien ways. The air we breathe would freeze solid and fall like snow. Water becomes harder than steel. Even hydrogen, the lightest element, transforms into metallic ice. This deep freeze creates surface conditions unlike anything found on planets orbiting stars, turning rogue worlds into cosmic laboratories for extreme physics. Deep inside rogue planets, nuclear furnaces continue burning long after their surfaces freeze solid. These internal heat sources can maintain planetary activity for billions of years. The heat comes from radioactive decay, the natural breakdown of unstable atomic nuclei within the planet's rocky core. Elements like uranium and thorium release energy as they slowly transform into lighter elements over geological time. This radioactive heating works like a cosmic battery that never runs down completely. The decay process generates enough energy to keep planetary interiors hot, even when surface temperatures approach absolute zero. Additional heat comes from leftover energy from the planet's original formation. When planets form, gravitational compression generates enormous heat that takes billions of years to radiate away completely. Together, these internal heat sources can maintain liquid water oceans beneath frozen surfaces, creating potentially habitable environments in the most unlikely places. Atmospheres can't survive on most rogue planets. The extreme cold causes atmospheric gases to condense and fall to the surface like cosmic snow. This atmospheric collapse happens because gas molecules slow down dramatically in the cold. When molecular motion decreases below a critical threshold, gases can no longer remain airborne and begin condensing into liquid or solid form. Nitrogen, oxygen, carbon dioxide. All the gases that make up planetary atmospheres freeze out at the temperatures typical of rogue planet surfaces. They form deposits of frozen air that accumulate like snowdrifts across the landscape. Only the lightest gases like hydrogen and helium might remain in gaseous form. But these gases are so light that they easily escape into space unless the planet has extremely strong gravity to hold them. The result is worlds with either no atmosphere at all or extremely thin atmospheric shells composed only of the most volatile substances. Thick ice crusts form the outermost layer of many rogue planets. These frozen shells can extend hundreds of miles deep, creating impenetrable barriers between the surface and any liquid water beneath. The ice forms from water vapor that was originally present in the planet's atmosphere or brought by impacting comets and asteroids. As temperatures plummet, this water condenses and freezes into solid ice that accumulates over millions of years. Unlike the thin ice sheets found on Earth, these planetary ice crusts are incredibly thick and permanent. They never melt because no external heat source exists to warm the surface above the freezing point. The ice isn't just frozen water. It includes ammonia, methane, and other compounds that were gaseous when the planet had a star. These mixed ices create complex layered structures with different properties at different depths. These massive ice shells effectively seal off rogue planets from space, creating isolated environments beneath that can evolve independently for billions of years. Liquid water can exist on rogue planets despite surface temperatures hundreds of degrees below freezing. This water hides in subsurface oceans protected by thick ice crusts. The key to maintaining liquid water is pressure and internal heat. Deep underground, the weight of overlying ice and rock creates enormous pressure that lowers water's freezing point. Meanwhile, heat from radioactive decay keeps temperatures above freezing. These hidden oceans can be vast, potentially larger than all of Earth's oceans combined. They exist in a dark, high-pressure environment completely cut off from the surface world above. The water in these oceans might remain liquid for billions of years, creating stable environments where complex chemistry could unfold. Dissolved minerals from the rocky core could provide nutrients for potential life forms. Some rogue planets might have multiple ocean layers separated by different types of ice, creating complex aquatic ecosystems stacked vertically throughout the planet's interior. Rogue planets with moons can generate heat through gravitational massage. This tidal heating process can keep subsurface oceans liquid even in the depths of interstellar space. Tidal heating works when a moon's elliptical orbit causes it to move closer and farther from the planet regularly. These distance changes create varying gravitational forces that squeeze and stretch the planet's interior. The repeated flexing generates friction within the planet's rocky layers, converting orbital motion into heat energy. This process can continue indefinitely as long as the Moon maintains its elliptical orbit. Jupiter's moon Europa uses this same heating mechanism to maintain a liquid ocean beneath its ice shell. Rogue planets with similar moon systems could sustain even warmer subsurface environments. This gravitational heating can be more efficient than radioactive decay at maintaining planetary warmth, potentially creating the most habitable environments found on wandering worlds. Most rogue planets lose their magnetic fields within a few billion years of ejection. This magnetic death sentence exposes them to the full fury of cosmic radiation. Planetary magnetic fields are generated by electric currents flowing in molten metal cores. These currents require convection, the circulation of hot liquid metal driven by temperature differences within the core. As rogue planets cool over time, their cores eventually solidify and convection stops. Without flowing liquid metal, the magnetic dynamo shuts down and the protective magnetic field disappears. Earth's magnetic field deflects harmful charged particles from space, creating the aurora displays we see at the poles. Rogue planets without magnetic protection have no defense against this cosmic bombardment. The loss of magnetic shielding affects any atmospheres or surface chemistry that might exist, allowing space radiation to gradually strip away remaining gases and alter surface materials. Volcanic activity can persist on rogue planets long after their surfaces freeze solid. These subsurface eruptions are driven by internal heat sources that operate independently of stellar warming. The volcanic heat comes from radioactive decay in the planet's core, plus residual heat from the planet's formation. These energy sources can drive geological activity for billions of years, even in the absence of external heating. Volcanic eruptions on rogue planets would look completely different from familiar Earth volcanoes. Instead of lava flowing across the surface, volcanic heat would mostly melt overlying ice layers and create temporary lakes or geysers. The eruptions could also create pathways for subsurface oceans to reach the surface temporarily, offering brief glimpses of the hidden aquatic environments deep within these frozen worlds. This ongoing geological activity helps maintain chemical diversity and energy gradients that could support complex chemistry or even life in the planet's interior regions. Seasonal changes don't exist on rogue planets. These worlds experience perfectly constant conditions that never vary with time or location. Seasons on Earth result from our planet's tilted axis and elliptical orbit around the Sun. As Earth moves through its yearly orbit, different regions receive varying amounts of sunlight throughout the year. Rogue planets have no star to orbit and therefore no external energy source that could create seasonal variation. Their energy comes entirely from internal sources that remain constant over geological time periods. The only variations in temperature and conditions occur with depth below the surface. Surface regions remain uniformly frozen while interior regions stay consistently warm. This creates stable thermal layers that persist for billions of years. This seasonal stability means that any processes occurring on rogue planets can continue uninterrupted for enormous periods, potentially allowing complex evolution in ways impossible on planets with changing conditions. High-energy particles from space constantly bombard rogue planets that lack magnetic field protection. This cosmic radiation can alter surface chemistry and potentially affect any life that might exist. Cosmic rays are charged particles, mostly protons and atomic nuclei, that race through space at nearly the speed of light. They originate from supernova explosions, black holes, and other violent cosmic events. When these particles strike rogue planet surfaces, they can break apart molecules, create new chemical compounds, and gradually change the composition of surface materials over millions of years. The radiation exposure on unprotected rogue planets would be lethal to most Earth-based life forms. However, some extremophile organisms on Earth can survive similar radiation levels, suggesting that radiation-resistant life might be possible. This cosmic bombardment also creates secondary particles and radiation when primary cosmic rays interact with planetary surfaces, creating complex radiation environments throughout the upper layers of these worlds. All rogue planets are gradually cooling down and will eventually reach complete thermal equilibrium with empty space. This represents a one-way journey toward absolute cold that no internal process can reverse permanently. The cooling process follows the laws of thermodynamics. Heat always flows from warmer objects to cooler surroundings. Rogue planets continuously radiate their internal heat into the near absolute zero temperature of interstellar space. Over billions of years, even the most massive rogue planets will lose most of their internal heat. Their cores will solidify, geological activity will cease, and any subsurface oceans will eventually freeze solid. This thermal death is inevitable but extremely slow. Massive rogue planets might maintain significant internal heat for over 10 billion years, longer than the current age of the universe. The cooling timeline determines how long rogue planets can maintain potentially habitable environments in their subsurface oceans before succumbing to the cosmic freeze. Extreme pressure deep within rogue planets creates exotic forms of ice that don't exist anywhere on Earth. These ultra-compressed ices have properties more similar to metals than to ordinary frozen water. The pressure comes from the enormous weight of overlying ice and rock layers. Deep within large rogue planets, this pressure can exceed anything found on Earth's surface by factors of millions. Under such extreme conditions, water ice transforms into crystalline structures with completely different properties. Some forms of high-pressure ice are denser than liquid water and harder than steel. These exotic ice phases can conduct electricity and have mechanical properties similar to ceramics or metals. They represent entirely new states of matter that exist only under the extreme conditions found in the depths of massive frozen worlds. The presence of these ultra-high-pressure materials could affect how heat moves through rogue planet interiors, potentially influencing the survival of subsurface oceans and geological activity. Life exists in places on Earth that seemed impossible just decades ago. These extremophile organisms survive in conditions remarkably similar to what we might find on rogue planets. Deep ocean thermal vents host thriving ecosystems in complete darkness. The water temperatures reach boiling point. The pressure would crush human bodies instantly. Toxic chemicals flow constantly from the seafloor. Yet these hostile environments teem with life. Bacteria, tube worms, and strange crustaceans have adapted to survive without any energy from the sun. They've developed completely different biological strategies than surface life forms. Scientists have also discovered life forms in Antarctic ice sheets, inside solid rock formations, and in highly radioactive environments. Each discovery expands our understanding of life's adaptability and resilience. These Earth-based examples suggest that rogue planets might not be the sterile wastelands we once assumed, but could potentially harbor their own unique forms of life. What if life could exist without sunlight? On Earth, some organisms have already figured out how to survive using purely chemical energy sources. This process is called chemosynthesis. Instead of capturing solar energy like plants do, these organisms extract energy from chemical reactions. They consume hydrogen sulfide, methane, or other compounds and convert them into usable biological energy. Chemosynthetic ecosystems exist completely independently of photosynthesis. They could theoretically survive even if the sun disappeared tomorrow, as long as chemical energy sources remained available. Rogue planets might have abundant chemical energy sources. Volcanic activity could release hydrogen sulfide and other reactive compounds. Radioactive decay could create chemical gradients that life forms could exploit. This means rogue planets could potentially support entire ecosystems based on chemistry rather than solar energy, creating alien biospheres unlike anything found on Earth. Beneath the frozen surfaces of rogue planets, vast underground realms might harbor complex ecosystems. These subsurface biospheres could remain active for billions of years. The key ingredients already exist. Liquid water oceans provide the essential medium for life. Dissolved minerals from rocky cores supply nutrients. Heat from radioactive decay provides energy gradients. These underground oceans would be completely isolated from surface conditions. They could maintain stable temperatures and chemistry for geological time periods, allowing evolution to proceed uninterrupted. Earth's deep subsurface contains extensive microbial ecosystems that extend miles below ground. Some of these organisms have been isolated from surface life for millions of years, developing unique evolutionary adaptations. Rogue planet subsurface environments could be far more extensive than Earth's underground biosphere, potentially supporting ecosystems of unprecedented complexity and diversity. Radioactive elements inside rogue planets act like long-lasting batteries that could power life for billions of years. These nuclear energy sources work independently of any external power supply. The radioactive decay of uranium, thorium, and other heavy elements releases steady streams of energy. This process continues for billions of years, providing consistent power regardless of external conditions. On Earth, some bacteria actually consume radioactive materials directly, using nuclear decay as their primary energy source. These radiotrophic organisms demonstrate that life can adapt to use even nuclear energy. Rogue planets might contain much higher concentrations of radioactive elements than Earth. This could provide more abundant and longer-lasting energy sources for potential life forms. The combination of radioactive heating, chemical energy, and thermal gradients could create energy-rich environments capable of supporting complex biological processes throughout a rogue planet's interior. Could rogue planets serve as cosmic arcs that transport life between different star systems? This panspermia hypothesis suggests wandering worlds might be nature's interstellar seed ships. The idea works because rogue planets travel through space over enormous distances. A planet ejected from one star system could eventually encounter another star system millions of years later. If the rogue planet harbored life in its subsurface oceans, those organisms could survive the long interstellar journey. When the wandering world enters a new stellar system, it might transfer life to other planets through impacts or atmospheric exchange. This process could explain how life spreads throughout the galaxy. Instead of requiring separate genesis events in each star system, life might propagate from system to system via rogue planet carriers. Recent discoveries of hardy Earth organisms that can survive space radiation and extreme cold suggest that interstellar life transfer might be more feasible than previously thought. Reaching rogue planets presents unprecedented challenges for space exploration. These worlds exist in the cold depths of interstellar space, far from any navigational landmarks. The first challenge is simply finding them. Most rogue planets are completely invisible to conventional telescopes, detectable only through rare gravitational lensing events. Planning a mission to an invisible target creates obvious navigation problems. Distance represents another massive barrier. The nearest known rogue planets are probably dozens of light-years away. Current spacecraft would require millions of years to reach such distant targets. Energy requirements for interstellar missions exceed anything achievable with current technology. Spacecraft would need power systems capable of operating for centuries in the cold vacuum between stars. These technical challenges mean that rogue planet exploration will require revolutionary advances in propulsion, power generation, and autonomous navigation systems. Unmanned robotic probes offer the most realistic approach for exploring rogue planets within the next few centuries. These automated explorers could survive the harsh conditions and enormous travel times. Advanced AI systems would need to operate independently for decades or centuries during the journey to distant rogue planets. The communication delays with Earth would make real-time control impossible. The probes would require nuclear power sources to survive the cold of interstellar space. Solar panels become useless in the darkness between stars, making nuclear reactors the only viable long-term power option. Sophisticated scientific instruments would need to detect signs of subsurface oceans and potential life from orbit or surface operations. This includes ground-penetrating radar, chemical sensors, and drilling equipment. Such missions could launch within the next 50 years as breakthrough propulsion technologies become available, potentially reaching nearby rogue planets within centuries rather than millennia. Telescopic observations from Earth might detect signs of life on rogue planets without requiring direct visits. These remote sensing techniques could identify biological signatures across interstellar distances. Infrared telescopes could detect excess heat from rogue planets that suggests active geological or biological processes. Life-supporting worlds might be slightly warmer than purely geological models predict. Spectroscopic analysis could identify atmospheric gases produced by living organisms. Even thin atmospheres might contain detectable traces of oxygen, methane, or other compounds associated with biological activity. Radio telescopes might detect artificial signals if rogue planets harbor intelligent life. Civilizations on wandering worlds might use radio communication or navigation systems detectable from Earth. Future space-based observatories with advanced sensitivity could conduct comprehensive surveys of nearby rogue planets, creating the first census of potentially habitable wandering worlds. Accessing the subsurface oceans of rogue planets will require specialized drilling technology capable of penetrating miles of solid ice. This represents one of the greatest technical challenges in astrobiology. Earth-based ice drilling operations in Antarctica provide proof of concept for the required technology. Scientists have successfully drilled through several miles of ice to reach glacial lakes. Space-based ice drilling systems would need to be completely autonomous and capable of operating in extreme cold for extended periods. The drill would need its own power source and waste heat management system. Advanced drill designs might use heated probes that melt through ice rather than mechanically cutting through it. This approach would be more energy efficient and less likely to contaminate the subsurface environment. Successful penetration of rogue planet ice shells could provide direct access to alien oceans, potentially revealing entirely new forms of life adapted to these unique environments. Within the next 30 years, dedicated space missions will revolutionize our ability to find and study rogue planets. These specialized observatories will locate thousands of wandering worlds throughout our galactic neighborhood. The Roman Space Telescope, launching in the mid-2020s, will conduct the most comprehensive rogue planet survey ever attempted. Its infrared instruments will monitor 200 million stars simultaneously for gravitational lensing events. Follow-up missions will use advanced propulsion systems to conduct flyby reconnaissance of the nearest rogue planets. These scouts will map surface conditions, measure internal heat sources, and search for signs of subsurface activity. Eventually, specialized lander missions will touch down on rogue planet surfaces and deploy drilling systems to explore subsurface oceans. These ambitious missions could provide humanity's first direct evidence of life beyond Earth. The roadmap for rogue planet exploration extends from current detection efforts through robotic reconnaissance to eventual sample return missions, potentially revolutionizing our understanding of life's prevalence in the universe.